morning. Now I'm taking you through a new topic titled the symmetrical components. Symmetrical components. What do we mean by symmetrical components? We are going to learn to understand what symmetrical components deals with through learning about what symmetrical faults and non-symmetrical faults are about. A non-symmetrical fault on a three-phase system is a fault that always give rise to unsymmetrical currents. So when you have an unsymmetrical fault in a three-phase system, it gives rise to unsymmetrical currents. And that is the current will be unequal in the lines with unequal displacement. That is what we mean by unsymmetrical fault. That current will be unequal. That is unequal line currents. Unequal line currents, and also with unequal displacement. So the magnitude will be unequal, and the phase also displacement will be unequal. Now, when the unsymmetrical fault occur, the current in the three lines will become unequal as well as the phase displacement. But unsymmetrical applies only to the fault itself and the resulting line currents. That means that unsymmetrical fault we're talking about, it only applies only to the fault itself and the resulting line current. The impedance, the constant, and the voltages, the source voltages, those ones are always symmetrical through the main elements. Now, let's look at a proper analysis of unbalanced condition in three-phase network. If you look at a symmetrical balanced system, it will give you this picture, this with displacements as 120 degrees between the phases. You understand? That one will represent a symmetrical balanced system with equal magnitude and that are equally spaced. This is balanced, symmetrical. That represents a symmetrical system that has equal magnitude and that are equally spaced. Then when we look at the other one, that is the one with the unsymmetrical phasor, we see the one in this fashion. That is something like this when there is a fault where, for example, you have the phase displaced at different angles that are not symmetrical to each other as we have it in the symmetrical system. You can see that the displacements are different. They don't have equal displacement. And the magnitude also can be different. That represents an unsymmetrical source. Now, in order to resolve a system like this, it is necessary to use a factor called the operator alpha. Operator alpha. That is the factor that you use to resolve it. Alpha is defined as an operator that will be taken through a position of a phasor anticlockwise through 120 degrees. So that means when it goes through 120 degrees, alpha is 120 degrees. It advances anticlockwise through 120 degrees. That is alpha. So for example, if we consider this particular diagram, this particular phasor representation, our EA is at angle 0 degree. So EAB, for example, if it goes through anticlockwise, from this to this, EB has advanced 240 degrees with respect to EA. So if our EA is taken to be at angle 0 degree, that is our EA is taken to be at angle 0 degree. That means the EB, that is after it advances, after the alpha operator advances 240 degrees, right? With respect to EA, EB will be EA at angle 240 degrees. While EC, don't forget that the alpha operator will always advance anticlockwise. So the EC with respect to EA is 120 degrees with respect to EA. So it will be EA at angle what? 120 degrees. That is with respect to EA. So if you look at it very well, our our EB can also be presented in this form because this is alpha squared. So our EB can be referred to as alpha squared EA. While our EC, that is advanced on alpha, is alpha EA. Right. So with this now, let us say, since this one forms a symmetrical balance system as it is, that means if it's formed a symmetrical balance system, that means our EA, which is EA at angle 0, which is EA, plus EB plus EC, that is, we're talking about the summation of the total of the phase voltages, EA plus EA alpha squared EA plus alpha EA. Right. If you bring EA out, you have what? 1 plus alpha squared EA. Of course, you can just put as 1 plus alpha squared. Right. And you know that normally this balance system, this phase is supposed to be, when you have the summation, EA into 1 plus alpha squared. Let's say 1 plus alpha squared. It comes back to 0 point. That is 1 plus alpha squared. Comes back to 0. So this will eventually be what? 0. Yeah, which is also 0. Of course, which also confirms the summation of all the three phasors added together, balanced symmetrical phase, which is also equal to 0. Then that means you can say that 1 plus alpha squared is equal to 0. You can bring the conclusion that 1 plus alpha squared is equal to 0, which is one formula that you have to take note of. 1 plus alpha squared is 0. Now,